Good morning to all. So today we are going to speak about advanced Lyapunov spectrum and chaos analysis in nonlinear dynamical systems. Myself Durga Jayashankar and I have Rohit RB and Sandeep SL with us. Before moving into the topic, let's see some basic terms. I know we all are familiar with this. So first, it is nonlinear systems. So the systems whose behavior is highly sensitive to initial conditions, which demands specialized analytical techniques beyond linear theory, is known as linear systems. And then the next is chaos dynamics. We all know this already, but let me just brief it for you. Chaotic behavior describes the unpredictable, irregular evolution of a system due to its sensitivity to initial conditions, where tiny changes can lead to vastly different outcomes. And understanding chaos is really critical for modeling complex phenomena in climate, developing secure communication systems, and optimizing engineered systems performance. So what is basically a bifurcation diagram? So it is a visual representation used in dynamical systems to show how the long-term behavior of a system changes as the control parameter is varied. So here in the image you can see that from the x value ranging from 1 to 3, it is a single line. So we can see that when the parameters value is around 1 to 3, it is fixed points. And then from around 3 to 3.5 we can see splitting of branches, which is denoted by period doubling, and after that it is a dense band which shows chaotic behavior. So a bifurcation diagram always displays where a system shifts from one type of motion to another as the parameter changes, and these shifts are called bifurcations. The next topic is Lyapunov exponent. So it measures how quickly the nearby trajectories in a dynamical systems diverge or converge over the time. So here in the image you can see that from around 1 to 4 the LLE value is less than 0. So if the LLE value is less than 0, then it denotes that the system is stable. And from around 9 to 10 you can see that the LLE value is greater than 0, so it is chaotic. And when it touches 0, for example around between 5 and 6 we can see that the LLE value touches 0 repeatedly, so there the system is periodic or quasi-periodic. Now let's just familiarize with some of the systems that we have used in the study. The first one is Newton-Lapenic system. It is denoted by x star is equal to minus alpha x plus y plus 10 yz, y star is equal to minus x minus 0.4 y plus 5 xz, and z star is equal to bz minus 5 xy. Here the x, y, z are the state variables, and then x star, y star, z star are the time derivatives of the state variables, and alpha and beta are the parameters. So here the chaotic behavior is experienced when alpha is equal to 0.4 and beta is equal to 0.175. So here from the plot we can see that it shows a butterfly-like chaotic attractor, which is typical of Newton-Lapenic system. It indicates loops, non-periodic motion, and sensitive dependence on the initial conditions are clearly visible. Ideal for illustrating modern chaos theory and nonlinear dynamics in advanced research presentations. And the trajectories do not fill in the space uniformly. Instead, they form complex string-like shapes with non-integer dimensions.
Comparative analysis and application. Comparative attractor geometry, Pauli versus Lorentz. Comparing the strange attractors of the Pauli and the Lorentz system, highlighting the diversity of chaotic structures even when both satisfies the condition lambda 1 greater than 0. Pauli attractor, characterized by interactive folded sheets and a unique quasi-two-dimensional appearance within the 3D phase space. Lorentz attractor, defined by its classic double-dot butterfly structure, a hallmark of earlier chaos research, and both the pictures represent the Pauli attractor and the Lorentz attractor are given below. Visualization and geometry. The strange attractor, visual evidence for chaos. Attractor geometry. In 3D phase space, chaos creates a strange attractor, a complex structure that's bounded, never self-intersecting, and never repeats. The orbit endlessly wind in the finite region, showing both expansion, that is chaos, and folding, that is boundedness. Strange attractors are fractal objects appearing in the system within positive largest lineup of exponent lambda 1 greater than 0, and the phase trajectory is given below. Oscillator system. The oscillar attractor is known for its elegant spiral shape in 3D phase space, where the trajectory never intersects itself or repeats, demonstrating complex but deterministic chaotic behavior. And there is a Rosler equation given, and its parameter we used to obtain a canonical chaotic regime, and the initial states were taken as 1 1 1 respectively for x, y, and z. Numerical integrations are used custom Ural based scheme and used 50,000 points for numeric robustness, ensures dense, accurate sampling of the attractor's geometry. Geometric and dynamical insight for the Roseless attractor. 3D phase space features. Spiral trajectory in 3D, expanding and folding, never repeating, always bounded. Attractor displays a periodic yet deterministic motion. Strange attractor. The image is given below. Bifurcation and chaos in the Rosler system. Key features in the Rosler bifurcation diagram. For small c, the system is stable with a fixed or periodic motion. As c increases, periodic doubling occurs, leading to a chaos. At a higher c, the chaotic region appears with occasional periodic window showing the order within the chaos. And here, the image is given for showing the chaos.
And the Lyapunov spectrum analysis of the roster system. In this roster system, both lambda 1 and lambda 2 remains at or below 0 for all rho. Lambda 3 decreases strongly negative as rho increases, and the chaos is detected here. This is the Lyapunov spectrum versus the rho for the roster system. The parameters taken is A equal to 0.3 and B equal to 0.1. This is the 3-parameter system. And the heat map of chaos. The heat map, an advanced data visualization mapping, and the average maximum Lyapunov exponent lambda 1 as a function of two system parameters A and B. The horizontal horizontal compartment is taken as A range and the vertical is B range. The heat map shows where Rosler system is chaotic and or stable. Chaos mainly appear more moderate to high values of A and B. Such map helps researchers to choose parameters and understand complex system behavior easily. And this is a heat map of the Rosler system where the chaos is occurring. An integrated Rosler system using a Euler based scheme, 50,000 steps is fine time grid for fidelity. This is a Rosler attractor showing on the figure. It will be enlarged on the next slide for specific visualization. And the parameters is chosen like A equal to 0.2, B equal to 0.2 and C equal to 10. In this, the attractor forms dense looping spiral that never repeats but stay bounded. It shows nonlinear feedback, creating a strange attractor. Small changes in starting point grow quickly and shows chaos. Scientific insights from this image is like the shape shows stretching and folding, the key sign of chaos. A positive Lyapunov exponent confirms chaotic behavior, and the motion is aperiodic but follows deterministic rules. And this is the chaotic image of the Rosler's attractor. And the bifurcations of the Rosler system is like the Rosler system was stimulated using a faster Euler method with NumPy. It's a library. And the parameter C was varied from the range 0 to 5, 5 to 10 and 10 to 15. After removing transients, local maxima and X were recorded to study a long-term behavior. In the diagram we can see that this at 0 to 5 stable or periodic motion is happening, no bifurcation. At 5 to 10 periodic doubling leads to chaos, a small amount of chaos. For C equal to 7 to 8 approximately. And for 10 to 15 fully chaotic motion is happening, and this is the bifurcation image of Rosler's diagram, Rosler's system. And for the backward time, like we changed the time dt in the equation to minus dt, and the bifurcation occurred by changing that is given like this. From this image, for like C equal to 0 to 5, the system stays stable with one main branch. For C equal to 5 to 10, small oscillations or splits start appearing. And for C equal to 10 to 15, more splits shows higher instability, the step size has to be reduced very small to show this bifurcation. Otherwise, the system will get collapsed or some what to say got exploded very fastly with small time steps. So the time steps is increased by reducing the dt very small, like 0.000005, like that much is reduced. For the backward, time reduces chaos and reveals the system's hidden stable structure, where the attractors behave like repellers.
So now let's just have a look at the code which generates the bifurcation diagram of the roster system. So we start by importing the basic tools we need. Here NumPy handles all the numerical computations and arrays. Matplotlib will take care of the plotting of a bifurcation diagram, and then from NumPy we import ngit, which allows us to compile Python functions for massive speedups. Now we define a function called Roseler step. This represents one single time step of the Roseler differential equations. Here we have three variables x, y and z, and the system evolves according to three simple differential equations with constants a, b and c. This has already been discussed before. And then we create another function called integrate Roseler. So this one will take the parameters a, b and c along with the time step and a total number of steps to stimulate. So we start the system with the initial conditions x is equal to 1, y is equal to 0 and z is equal to 0. And then we create an empty array to store all the x values as the system evolves. And then inside this loop we repeatedly call Roseler step to update x, y and z at each time step, and after each update we store the new x value. So by the end of the loop we have a long sequence showing how the x changes over time. And finally comes the plotting part. So like here we create a matplotlib figure with three subplots stacked vertically. Here each subplot will show a different range of c values. The code loops over three intervals of c, from 0 to 5, 5 to 10 and then from 10 to 15. And for each range it generates around 800 evenly spaced c values. Within the loop each subplot is created using plt.subplot, and then we have used scatterplot to draw these points. As a result, this is the plot that we have, and it's already been explained by Rohit. So next, let's just have a look at the code where we compute the maximum Lyapunov exponent for the Roseler system and visualize where the system becomes chaotic in the parameter space. So like we start the usual imports, NumPy, Matplotlib and then NumPy ngit, and then we define a small function called Roseler step, which has already been discussed before. And then coming to Lyapunov max functions, this function basically estimates the largest Lyapunov exponent. Inside the Lyapunov max function, we start with the initial condition like x is equal to 1, y is equal to 0 and then z is equal to 0. We create a 3x3 identity matrix which we'll call it as Q. So this matrix is used to track how small perturbations evolve, and we also create a zero array named LE, which will store the running sum of the logarithms of the stretching factors. And now coming to the main loop, which runs for the specified number of time steps. At each time step we first compute the Jacobian matrix labeled J. So this matrix represents how small changes in the variables x, y and z affect each other. The entries of the Jacobians comes directly from taking partial derivatives of the Roseler equation with respect to each variables. And then once we have the Jacobian, we'll update the Q matrix using a small time step multiplication. So this effectively stimulates how a small cloud of nearby trajectories stretches in a phase space. Then we apply the QR decomposition, which breaks the Q into an orthogonal matrix and an upper triangular matrix R. Then the diagonal elements of the R represents how much stretching occurs along each orthogonal direction during this step. And we also take the logarithm of the absolute values of those diagonal elements and then add them to the running total LE. This gradually accumulation gives us the total stretching over the entire integration. And after processing the Jacobian, we move to the Roseler system forward one time step by calling the Roseler step. This updates the main trajectory while the Jacobian continues to track how deviations would evolve. And once all the steps are complete, we return the largest Lyapunov exponent. So a positive value here means that the nearby trajectories diverge exponentially, which indicates chaos. Next, we define the parameter ranges for our study. So we choose 6 values for the parameter A from 0.1 to 0.4, and then 6 values for B from 0.05 to 0.2, and then we take 20 values for C from 5 to 15. and then we'll create a two-dimensional numpy array called lambda max initialized with zeros. So this array will store the average maximum Lyapunov exponent for each combination of a and b, and each entry will correspond to one point on a heat map later. So now comes the computational loop. Like we go through each value of a, and for each a we loop through every value of b, and inside that we run another loop over all the c values. And for each combination of parameters, we call the Lyapunov max to compute the largest Lyapunov exponent, and then we add up all the values and take the average over c, and finally the average result is stored in the lambda max matrix. So this gives us a broad picture of how chaotic the system is for different pairs of a b averaged over a range of c. So once all these calculations are done, we move on to the visualization part. So we create a matplotlib figure and displace the lambda max as a matrix as a heat map, and then here the areas with the positive values are shown in red. It represents chaotic regions where the trajectories diverge rapidly. Negative or nearly zero values indicates stable or periodic behavior where the trajectories stay close to each other. So this is the image that we got. So now we are going to generate a bifurcation diagram of the Rosler system, but there is a slight difference. We are integrating the system backward in time. So like previously we start with the standard imports, and then we define the Rosler step function, and coming to integrate Rosler backward function. So this function basically integrates the Rosler system in reverse time. Which means that instead of moving the system forward step by step, we just use a negative time step to trace the dynamics backward. So this approach can basically reveal the stable structures in the system like attractors from a different perspective, and can sometimes make the chaotic patterns more stable and visually distinct in the bifurcation diagram. So inside this function, we start by setting the initial conditions for x, y and z. We choose x is equal to 1, y is equal to minus 0.2 and z is equal to 0.3. So like we can see that this is not a perfectly symmetric thing, right? Because previously we had 1 0 0, here we have 1 minus 0.2 and 0.3. So this small asymmetry helps the backward time integration avoid falling into overly symmetric trajectories or degenerate orbits. We also create an empty numpy array to store all the x values as the system evolves. And then for each time step, we call the Rosler step with a tiny negative dt. So this is what makes it run backward in time. And because the backward integration can sometimes become unstable, and especially for chaotic systems, we add a small stabilizing technique called a soft clamp. So like if any of the variables x, y or z grows beyond a reasonable limit, say for example if it is larger than 100 in magnitude, we reset them to the initial conditions. So like this prevents the simulation from blowing up numerically and keep the trajectories meaningful. And after each step, we store the new x value in the array, and after the loop we return all the stored x values. So next we define the bifurcation data backward function. So this function generates the actual data points for the bifurcation diagram just like in the forward time version, but now using the backward time integration which we described before. So like we start by setting up two empty lists, one for the c parameter values and one for the corresponding x values at the steady state, and then we loop over a set of c values, and for each c we integrate the Rosler system backward using our previous function. We then discard the transient part of the data. And once we have the stable part of the trajectory, we look for local maxima in the x values, like the points where the x rises and then falls again. And every time we find such a peak, we record the current c value and the corresponding x value. And these local maxima act as a kind of fingerprint of the system's oscillation. And plotting these peaks against the c gives us the bifurcation diagram. And in regions where the system exhibits periodic motion, we'll see just a few discrete points per c value, and for chaotic regions the points spread out densely, filling vertical bands. And now we can generate the bifurcation data. We move on to the plotting session. Like we create a large figure with 3 subplots stacked vertically, each one focusing on different range of the parameters from c, from 0 to 5, 5 to 10, and then from 10 to 15. So like this breakdown makes it easier to visualize the fine details of the bifurcation sequence. And for each range we generate around 600 equally spaced c values and call the bifurcation data backward function to compute the data. And then on each subplot we create a scatter plot of the results. This is the graph we got, and that's all about the coding part.
And we have to complete this project, like we have lots of things to do, like to compute the Lyapunov spectrum in the reverse time from different starting points, skipping the forward transients to avoid the false results, and during backward integration note when the trajectory becomes unstable and rate that time to how chaotic system is, and test across many parameters value to see patterns. Systems closer to the regular motion stay stable longer in reverse time. And these are the references we taken from of some papers. And thanking Dr. Denis Butso and Dr. Vyacheslav Rybin and Dr. Shashanka Muni for assisting us on the project, and thank you.